This video is an examination of length contraction within relativity theory. Normally, length contraction is thought to be a simple and basic idea and is not given much analysis. But length contraction is very powerful and is one of the three principles of relativity theory: length contraction, time dilation, and failure of simultaneity at a distance. An understanding of length contraction ultimately will lead to an understanding of how acceleration is analyzed within relativity theory. Not only dynamic acceleration, but gravitational acceleration. The paradox presented in this video is also called the ladder paradox in other texts. This thought experiment starts with a man standing stationary outside a garage, and he's holding a ladder. As you can see in the illustration, the ladder is longer than what the garage is. So the man cannot fit the ladder within the garage. The man starts running toward the garage, and when he gets up to a constant speed, you can see that the ladder is now shorter. The energy that is put into the man and the ladder in order to achieve the speed we will call energy Ke. This energy does not come from the man. This energy comes from the reference frame in which the garage is stationary. Initially, the garage door is open, but as the man runs inside the garage, as the illustration shows, a friend shuts the door behind him instantaneously, and his situation is now what you see pictured. He's inside the garage, still running, and still has energy Ke. Once the man gets inside the garage and the door is shut, he now stops running, and the ladder reverts back to its original dimension. So the ladder will naturally smash through the walls of the garage, and the energy that is required to do this smashing is going to be called energy Se. If we do an energy balance of this simple experiment, the energy input by the garage reference frame to get the man up to speed is Ke. The energy recovered by the garage reference frame when the man decelerates back down to speed 0 is Ke, and the energy delivered to the garage reference frame when the ladder smashes through the walls of the garage is energy Se. So as you can see, the total energy of the experiment is not equal to 0. In fact, energy Se has been created, or so it seems. But can this energy Se actually be created by this experiment? The answer is no. This experiment does not violate the law of conservation of energy, and energy Se has not been created by the experiment. What is pointed out by the experiment is the necessity of being precise in your analysis of experiments within relativity. The way the experiment should be analyzed is to look at this paradox through the eyes of the man who is running with the ladder. So, we will view the experiment as observers sitting on the ladder while the man is running. We see that the ladder is now its original length, and the garage is moving towards the ladder, and the garage is shorter. This leaves us with two options for what the man does next. The running man's first option is to stop short of having the ladder hit the back wall of the garage. But as you can see, if the man does this, he will not be completely inside the garage. The second option is to have the man continue to run until the back end of the ladder is inside the garage. But we can see in the illustration what happens here. He smashes through the back wall of the garage with the ladder long before the door is shut behind him. So this gives us a clue as to what's happening. The energy, SE, that we thought was created by the experiment was in fact coming from the man running into the back wall of the garage. So this view of the experiment cannot possibly happen. If the back wall of the garage is left intact, the man never gets through the door of the garage. If he does go through the door of the garage and it's closed behind him, the back wall of the garage is already smashed. So let's analyze this false view of the experiment further. We now put 3 clocks on the ladder. One in the middle of the ladder with the man reads, let's say, 12 o'clock when he's at this position within the garage. Then the other clocks on each end of the ladder read different than his clock. This is failure of simultaneity at a distance. So the clock at the back of the ladder reads later than 12 o'clock, and the clock at the front of the ladder reads earlier than 12 o'clock. So now that we've placed clocks on the ladder, let's review the options available to the man. In the first option, the man is going to stop at 12 o'clock. And so what that means is that the clock on the back of the ladder must also read 12 o'clock when the back of the ladder stops. So the back of the ladder stops before the man stops, as viewed by the observers who are in the same reference frame as the garage. This is what you see here. The back of the ladder has already stopped. The man keeps running until his clock reads 12 o'clock, then he stops. Then the front of the ladder keeps expanding out until it narrowly misses smashing through the wall of the garage. For option 2, let's assume that what happens is what is shown in the illustration. The back end of the ladder gets just inside the door and the door is shut. The man is able to stop just in time before the front of the ladder breaks through the back wall of the garage. The back of the ladder has already stopped, and in fact all of the rungs of the ladder up to the man have stopped because the man has stopped at 12 o'clock. But the front of the ladder hasn't gotten to 12 o'clock yet. So the front of the ladder keeps going and eventually smashes through the back wall of the garage, even though the man has already stopped. The first thing to notice is that the back end of the ladder does not smash through the garage door. The back end of the ladder has already stopped by the time the man has stopped running at 12 o'clock, and so the garage door is not damaged. What does happen is the man is stopped, but the front end of the ladder is still moving forward because the front end clock has not gotten to 12 o'clock yet. So it is the front end of the ladder that smashes through the back wall of the garage, and that gives you an idea of where energy SE comes from. The man has stopped, the back end of the ladder has stopped, but the front end of the ladder still has its own portion of KE, and it's this portion of KE that is converted into smashing energy SE. So now we can do the actual energy balance for the length contraction paradox experiment. The energy to get the man and the ladder up to speed is still KE, but the energy recovered when they stop again is not KE, because it's only the man and the back half of the ladder who have stopped on their own. The front half of the ladder gives up some of its energy to smashing the garage wall as it keeps extending after the man has stopped. So the energy recovered when the man and the ladder stop again is only KE minus SE. And the energy to smash through the wall, of course, is still SE. The energy created by the experiment, therefore, now adds up to 0, and the law of conservation of energy remains intact. So even though the energy of the experiment is no longer an issue, we're going to go back to the middle stage of the experiment and look at it a little closer. What we see here is the man running inside the garage with the ladder and the 3 clocks on the ladder. Now we said this can't happen in the experiment, but the truth is it can happen in the experiment. It can happen if the man never intends to stop running. If he intends to run straight through the garage and smash through the back wall without stopping at all, without changing his velocity, then this view of the experiment is perfectly valid view. Now, the garage observers cannot shout ahead and say, "Hey, I know you're going to stop, so keep running." They can't do that. That's impossible. However, what you should be saying to yourself is, we're reading the man's future here. We know what he's going to do before he does, in a way. So there's a lot more information that's available here than first meets the eye. In other words, length contraction, time dilation, and failure of simultaneity at a distance is pretty complicated, and we should ask ourselves, how do we know more? This is a complex situation. It's not the simple experiment we first laid out. There's a lot more information. How do we find out exactly what's going to happen with that accelerating ladder? The real paradox of this experiment is that nobody can tell you what's happening on that ladder. Even 100 years after length contraction has been a recognized principle of relativity theory. We now know we can look at the back of the ladder and know what the runner is thinking even before he thinks it. So is it possible to use that information? You would need a precise equation for what the clock reads on the back of the ladder versus what the runner's clock reads in order to know if you can use that information somehow. But those equations don't exist. You might ask yourself, what other options for the experiment exist other than the option 1 and option 2 presented in this video? Or you might ask yourself, how fast is the front of the ladder going when it smashes through the back wall of the garage? But traditionally, relativists tell you length contraction is only dealt with in inertial reference frames, in constant speed reference frames. When you say, okay, let's consider acceleration, the answer is usually something like, oh, that's way too complicated to analyze. And it is complicated if you try to consider all of the possible acceleration experiments that could be dealt with. But, as it turns out, the most important case of acceleration of objects with length is also the easiest to analyze. That most important case is constant acceleration in the direction of the length of the object. And the solution of that constant case is this equation, where alpha is the acceleration of a location on the ladder. For example, if the length of the ladder is L, the acceleration of the front of the ladder is given in terms of the acceleration of the back of the ladder, and c is the speed of light. Now some people might say, wait a minute, the front of the ladder can't have a different acceleration than the back of the ladder, but of course it can. If you look at the inertial case, the reading of the clock on the front of the ladder is different than the reading of the clock on the back of the ladder. It's the same for acceleration. Everything is varying down the length of the ladder, and this equation tells you precisely how that variation occurs, including clock readings, lengths, coordinates, whatever you need to know. The good news is, once you know this equation, you're already about halfway to understanding how relativity treats gravitational fields, because gravity is also an acceleration. But it's a lot easier to deal with this equation and its gravitational brothers than it is to deal with general relativity. And in fact, this family of equations will tell you everything that general relativity can tell you, but at only about 1% of the work. So this is a very handy little equation to know. For more information, see the article, The Real Ladder Paradox, on the website www.newrelativity.net.